Hello guys, welcome to a new video. Today I'm going to be talking about recurrent neural networks, and in this channel I'm going to be uploading videos on physics, numerical methods, and also machine learning, three areas I'm very interested in. And today we're going to be talking about recurrent neural networks, and we're also going to give a brief explanation of them and an implementation. So a recurrent neural network, for those who don't know, is a type of deep learning architecture that is really useful when you want to predict sequential data. Initially, in the 2010s, for example, neural networks were designed under the assumption that each instance in our training data set was independent of each other. But as we know in the real world, this is false because there are multiple types of data that are dependent on the previous time steps. To give you an example, we have stock data. The price of a stock is dependent upon the previous price of a stock. It is not completely independent of each other. Moreover, if we imagine words in a sentence, they depend on context and other semantics, so they are not independent of each other. And recurrent neural networks were proposed as an architecture that could solve this by keeping an internal state that would keep track of the temporal dependencies between data. So as we can see in this scheme in this schematic right here, on part A, we have a recurrent neural network cell. Now, the layers of recurrent neural networks are comprised of multiple recurrent neural network cells, and the way it works is very simple. At some time step, we're gonna have an input that's a x of t, and it goes into our we can imagine this to be a neuron, and the neuron takes in two inputs, our input feature vector, as well as some hidden state h of t minus 1. H of t minus 1, as we can notice, it depends on the previous time step. And our neural network is symbolized on this right here. And as you can see, h of t is a function of phi, and it has two parameters, h of t minus 1 and x of t, which is our observation at time t and our hidden state at a time t minus 1. And it gives us some output y of t. At the next time step, the new computed h of t, which is given right here, is fed into the next time step to conduct the computation. So as we can see, h of t is defined to be the hyperbolic tangent of the weight matrix multiplied by the previous hidden state plus another U matrix which contains weights for the inputs, x of t. And y of t is simply the softmax of our weight matrix for the output layer multiplied by the hidden state. And in figure B, we can see this recurrent neural network cell unrolled. So first, imagine we have some initial time step and some previously hidden time step. Now in practice, this initial hidden time step can be initialized to just zeros, empty, or random numbers. It just has to be an initial guess. And so we input our observation as well as our previous hidden layer, our previous hidden state, and we get some output y1. And then this newly computed hidden state is fed into the next time step, and so on successively. Now that's a brief overview. In the description, I'm going to list some very useful articles that can give you a more in-depth explanation of the mathematics behind recurrent neural networks, as well as a brief historical background. Now, the next part of this video, we're going to implement one using Python and TensorFlow to predict the price of a stock. In this case, we are going to be looking into SBUX. All right, so now that we are here on our Google Colab notebook, we're going to begin our implementation of a recurrent neural network. Now, let's remember that recurrent neural networks are architecture used when we are dealing with data that has a temporal dependency, or each successive observation depends on the previous observations. Now, it is important to keep in mind that recurrent neural networks are architectures that are now being replaced by novel, larger architectures like transformers, um, and some transformers, or there are even variations of recurrent networks, which we're going to explore in future videos, including LSTM or gated recurring units, which are architectures that attempt to fix an issue that is commonly present when we are trying to um, compute very deep recurrent or train very deep recurrent neural networks, which are vanishing gradients and also exploding gradients. Those were the two problems that were initially plaguing the vanilla recurrent neural networks, but it was solved by LSTM, GRU, and other variants. Now, in this video, we're just going to be dealing with vanilla recurrent neural networks, but in future videos, if you guys want, we can explore LSTMs for other use cases. Now, going back to our task, today we're going to be predicting the stock price of Starbucks using historical data. Now, the only feature we're going to be using it is the closing price. We're going to ignore volume, the open price, as well as the highs and lows. Those are very important features that are used when you're doing quantitative research, but for the purposes of this video, we're just going to be looking at the closing price of the stock price starting in the year 2014. So we have a data set that was downloaded from Yahoo Finance. I'm going to link it on the description as well. And so we have two inputs, namely the date and the closing price. So what we're going to do is we're going to feed a portion of our data into the model, and we're going to teach it to forecast the next closing price. And we're going to divide our data into batches of 50. So the way it's going to be trained is that a batch of 50 is going to be trained into a batch of 50 is going to be fed into our neural network. And based on those 50 observations, our neural network is going to attempt to make a prediction for what should the next closing price be, and so on and so forth. So first, we begin by, of course, importing our data using pandas. Now, this is the name of our CSV, and I have it here on our Google Colab storage. And so if we want to read the head, we can see that we have the date, the closing price, volume, open, high, and low, and it starts in 2024, and it ends on it starts in 2024 because the data is the first row is the most recent observation, and the last row is the oldest observation. Now, in order to properly train a neural network, we have to do a little bit of data pre-processing. First, we have to get rid of these money symbols. So we do that using the .replace method, and we also have to convert it to a float. Besides that, we have to reverse it so that the first observation is the oldest observation in our data set, and so on and so forth, and the last observation being the most recent one. And we also want to reset our indexes so that it's easier for manipulation purposes. After we have done that, we can see that the first observation is now the oldest one on our previous data set, and we have gotten rid of the money symbols. So now we have to do the train test split. The length of our data is needed to compute the length of our train data, which is we're going to use 70% for training data, 30% for validation. Okay, and so as we can see, pretty simple. You do some standard data test splitting. We're not using a validation data set. We're not using, and in this right. So as we can see, we have a total of 2,500 observations approximately, and our training data length is going to be of 1,763, and our validation of 755. So 30% is going to be for validation. Now here we can take a closer look at the data set that we're going to use. Just again, date and closing last. We're going to ignore the other features. And as we can see, just our data set starts at 2014, ends at 2021. The validation starts where the training data set left off and ends on 2024, January 5th. And okay, we have to reshape it so that it becomes a two-dimensional NumPy array of first dimension having 1763. That simply means 1,763 rows and just one column. Now we want to scale out our data to improve the performance of our model, and we do that using the min-max scalar function from sklearn. Well, it essentially makes is it maps every observation in our dataset, in this case a price, to a range between 0 and 1. And if we plot it, we can see that the stock price looks like this. It looks like a standard time series chart for stocks. Okay, now we can create our X and Y train arrays. And now, as I mentioned at the start of the video, we're going to divide our training and validation data sets into steps of 50 because our model is going to train to predict the next one following the 50 time steps. And we do XY train, we convert it into NumPy arrays, and we reshape them. As we can see, the X train is going to be a two-dimensional NumPy array of with 1,713 rows and 50 columns, and the shape of our target array is going to be of the shape 1,713 by 1. Now we have to make this explicit, and we have to make this into a three-dimensional tensor in order for it to be compatible with TensorFlow. And so we're going to be using the standard libraries from Keras, namely sequential, dense layer, a simpler recurrent neural network, and dropout. So we're going to call our model regressor, and as we can see, it's a simple sequential model. A sequential model is, for those who don't know, is just a very basic model that stacks layers sequentially. In a future video, I'm going to try to make a comprehensive tutorial of TensorFlow, so please subscribe if you are interested in that. And so the first thing we're going to do is we're going to add a simple recurrent neural network layer, and the output of this first layer is going to be 50. So we can imagine that we have 50. So we can imagine that we have 50 neurons in our layer, and the activation for each neuron is going to be a hyperbolic tangent. And here we simply specify our input shape, which is going to be a vector of 50 rows in dimension 1, and we add some dropout. Now we add a second recurrent neural network layer with again 50. It's pretty similar to the first one, and also dropout. The third one, pretty much the same. And the fourth one is just another one, a simple recurrent neural network layer. Again, output 50 and dropout. And last, we add a dense layer that is going to give us our prediction for our last. This is going to give us our prediction. So the final output layer is the dense layer. As we can see, it only has one neuron because we only need one weight. We only need one output. In this case, it would be the next stock price given some 50 previous stock prices. Now, we simply use the thought summary method to have an overview of our architecture, and as we can see, we have quite a complex architecture. We have a total of 17,801 trainable parameters. And here is a simple image of our architecture. Now we can compile this model using the .compile method, again from TensorFlow and Keras, and we are using our Atom optimizer, and we use the L2 loss, and we are going to be targeting for accuracy. Now the ADAM optimizer is simply some gradient-based optimizer that conducts gradient descent. And then we just fit the model. We want to find the mapping between our training data and our training targets. We can do this for 50 epochs, meaning that our model is going to see all of our data 50 times on a batch size of 32. All right, and after training that, took about 5 minutes, we see our simple recurrent neural network model and the loss versus the function. As we can see, this is pretty standard. Okay, and now we want to test our model by conducting some prediction on the training data, and then we want to see our Y prediction, and we get this visualization. This is simply telling us how well the model does on the training data as it's training. As we can see, it's pretty accurate. On the last part of this notebook, we're gonna actually see the accuracy of our model. So now let's say we want to validate it, or in other words, test our model on previously unseen data. So in order to do that, we have to do the same thing we did with our training data set, which is converting it into a time series of 2 dimensions of 755 columns. Sorry, 755 rows, 1 column, and we create our test set and our target test set, which is what we're going to use to plot the predictions of our model and the actual data. Okay, and here we do the same thing. In other words, this is our predictions based on our testing data set, and then we reshape it so that it has one, so it becomes a 2-dimensional NumPy array. Now here, this is what we're essentially interested in, the performance of our model against actual data. As we can see, the model is able to capture the general trend of the stock price data, but it fails to effectively capture the daily volatility of the stock. Now, if we were to, let's say, propose this to a value investor or passive investor, then this might be a sufficient model because it's just capturing the general trends. And of course, value investors are not concerned with the short-term behavior of the stock market. But if we were to propose this to, let's say, a day trader or someone who's concerned with high frequency trading, this model would be useless because it's unable to capture the second to second or daily open close price of a stock. But of course, this model can be better by modifying architecture or considering more sophisticated variants like LSTM or GRU variations, which I hope to make a video of in the following days. Now, if we put together, we can see that in general, the model performed relatively well for the simplicity of it, which is surprising. And actually, Andrej Kartpathy talks about this in a blog post. I would definitely recommend you check it out because he also talks about the surprising effectiveness of recurrent neural networks, especially very simplistic models relative to their performance. Now, if we are interested in seeing the metrics, we can see that the root mean squared is about 2.64, meaning that, and this value is in the same units, in this case dollars, so meaning that our performance is it's off by about $2.64, either up or down. And this is the metric we were interested in, 97.90, meaning that our model had about 98% accuracy, which is pretty good for a simple model as we saw in this video. Okay, so that brings us to the end of the video, guys. If you enjoyed it, please like and subscribe the button. Please. Alright, guys, and that brings us to the end of the video. If you enjoyed it, please like it and subscribe. Also comment if you have any suggestions as to how to improve this model, or if you need help with anything else. As I have mentioned in my previous videos, I'm interested in physics and numerical methods and machine learning. And physics specifically, please follow my series in which I'm going over the problems, in this case, of the textbook Griffiths of Quantum Mechanics. Without further ado, please hit that like button, subscribe, and until the next one.